Yo, what's up everybody? Okay, so today I'm going to show you 6 Lewis structures, and this is for people who've like zoned out during class or missed some classes or just don't still understand what's going on. So we're going to go through some Lewis structures today just so that you're good at this. And the first thing I want to show you is how to determine what your center atom is. So let's look up here, right? I got 6 different structures. The central atom is super easy. Whichever one you have only one of is usually your center atom. So CBr4, I have 1 C and 4 Brs. That means C is my center atom. I go here, same thing. C, I only have 1 C, so C is my center atom. Down here, I don't have a central atom. There's only 2 atoms bonded together. There's nothing in the middle. So Cl2, no center atom. Let's keep going. H2S. H2S, 2 H's, 1 S. S will be in my center. Here, N will be in the center. And here, O will be in the center. So hopefully that makes sense for how we determine which one's the middle. After we determine which one's the middle, now we're going to actually draw the structure. So let's do valence electrons first. Let's start with carbon bromide here. So carbon is going to go in the middle. And carbon has 4 valence electrons. Because of hybridization, we're going to spread them out. So that is carbon, and that's carbon's 4 valence electrons right up there. Now, carbon wants 4 more. It has 4. It wants 4 more to get to 8. Your goal here is to make everything of 8. So if carbon has 4 and wants 4, if it wants 4, that means 4 bonds. Carbon wants to share 4. Every atom, every electron that carbon shares gives it another one. So if carbon shares 4, it gets 4 more, and it gets up to 8. Wants 4 electrons, needs 4 bonds. Here we go. Bromine is going to go around carbon. So 1 bromine on each side. We're going to connect the dots. Let's do it. 1, 2, 3, 4. And now I have bromine here, bromine here, bromine here, and bromine here. With the valence electrons on bromine, we will have to consider them just for the Lewis dot structure. So each bromine has 7 valence electrons. And because it has 7, it only needs 1 more. If it needs only 1, bromine can only make 1 bond with carbon. So drawing the valence on bromine, I have 3 pairs of them on each. So I have 6 valence electrons here, plus my 7th right here, and then carbon's giving it its 8th. So that's how CBr4 looks, and this is how it works. So to finish it up here, this is my Lewis dot structure of carbon tetrabromide. What I'm going to do now is show you the bond angles, and I'm going to show you the shape, and then I'm going to show you hybridization. We're going to do polarity in the next video. So, carbon tetrabromide. If I draw the shape really quickly, I'm going to start with my center atom and just make it a sphere. And then I'm going to do 4 bonds around it. So, in 3 dimensions, this is making a tetrahedral shape. It's like a tripod with a little thing coming up. So this is a tetrahedron right here. And we call this tetrahedral for the behavior. And the bond angle is going to be in a tetrahedron 109.5. So this bond angle here is 109.5 degrees. And that's how we do a tetrahedron. Now, how many regions of electrons are there? There's 4. 4 regions of electrons for hybridization means I need 1 s and 3 p orbitals to get a total of 4 areas of electrons. So sp3 is your hybridization here. sp3, there you go. Hopefully this one makes sense. We're going to get a little harder now, so we're going to go to CO2 next. CO2 is going to have the carbon being in the middle, so let's start there. carbon is going to go in the middle. And what we're going to do is put oxygen one on each side. Carbon has 4 valence electrons, and oxygen has 6. 1, 2, 3, 4, 5, 6. Oxygen here, 1, 2, 3, 4, 5, 6. Okay. You can see here that if carbon single bonds with oxygen, I still have this guy left over. Oxygen needs two more valence electrons. If oxygen needs 2 more valence electrons, it wants to do 2 bonds. But I only got 1 on each side. So oxygen is going to have to double bond. So what's going to happen to carbon here is the valence electrons are going to move. They're going to move, and they're going to line up here with the oxygens. This same thing is going to happen with the oxygens lone pairs. The valence electrons here are going to move until they're also lined up with the carbon. So we're now going to connect the dots and make 2 double bonds. Oxygen gets 2 over here, and carbon gets 2 more from this oxygen. And when we go this way, the carbon will get the other 2 it needs from this oxygen, and this oxygen will be happy. So carbon starts with 4, and it needs 4. 2 come from this double bond, and 2 come from this double bond. So hopefully that makes sense. Now, clearly here, carbon is my central atom. Carbon has no lone pairs. So the shape here is going to be pretty linear. I'm going to show you how this is drawn. So sphere in the middle with my little double bond with another sphere and another double bond with another sphere. There's my linear shape. And my angle's 180, so I'm going to be linear. And I'm going to be 180 degrees. There's my bond angle. The last thing is going to be hybridization. And we have right here how many regions of electrons? Well, I got a bond here and a bond here. Even though they're double bonds, it's still one region where electrons are. So we're only going to have 2 regions of electrons. One here and one here. 2 regions of electrons means I have sp hybridization. Because 2 regions, one in the S, one in the P, and they combine. So your hybridization here, sp. Done. Let's go a little faster now. We're going to go to Cl2. Now, there's no central atom here. All we know is that we have Cl and we have it twice. 2 Cl's. Let's just put them next to each other. Here we go. We're going to stick the valence electrons around the chlorine. So when I do that here, I have 7 on each. And then I have 7 on this one. And voila, look at that. They can share 1. Chlorine wants 1 more, so 1 bond. However many it wants is the amount of bonds you need. So the Lewis dot structure, we're just going to connect these dots. Yay. So chlorine is happy. Chlorine doesn't really make a shape here. It looks linear, but because there's only 2 atoms and there's nothing in the middle, there's nothing to make an angle around. So no shape, no bond angle, and no hybridization. Technically, the Cl's are each sp3 because there are 4 regions of electrons around each Cl. But because there's no center atom, I'm not going to do hybridization for this one. So we're only going to hybridize central atoms. Now I'm going to scooch this way, and we're going to keep going. So up here I have H2S. H is weird. How many does H want? 2. Dose, not 8. H is fine with 2. H has 1, needs 1. H can only single bond. Sulfur is my middle atom because there's only 1 of them. So let's start with sulfur. Let's draw it out. So sulfur is here. The glare is horrible there, but there's sulfur. Let's give sulfur its 6 valence electrons it needs. 1, 2, 3, 4, 5, 6. I just put them there, but they're going to be moving around. So with sulfur, this is weird. If you build sulfur using your sphere models, you're going to find that the lone pairs and the bonds are both next to each other. So how does this work? Well, I got 2 lone pairs here and 2 loners. Anytime you see a loner, you need a bond. You can't have loners, that's bad. So sulfur has 6, wants 2, so 2 bonds. Specifically, there are 2 hydrogens, so 2 single bonds, 1 with each hydrogen. And that'll get sulfur to 8. So watch this. I'm going to put the H's in blue. I'm going to have an H here. I'm going to have an H here. We're going to connect the bonds. And that might look good for some people, but here's the problem. When we draw the shape, this is not what it looks like. These lone pairs are going to take my linear bond and bend it into like a V-looking shape. So what we're going to do here is take this shape and move the lone pairs up. So this lone pair and this lone pair are going to go next to each other. So we're going to have 1, 2, 3, 4. The bonds are going to repel the lone pairs. So instead of the H's being here and being linear, the H's are going to be bent. So each H now has 2, and the sulfur here has 6, and then it's sharing 2. So sulfur has 8, hydrogen has 2, we're having a good day. How does this look shape-wise? Well, here you go. So the shape looks like so. Here's a sphere, okay? I got 2 sets of lone pairs, 1 here and 1 there. Now I need the bent structure, so let's bend it. There you go. Sphere, sphere, and now I'm bent. What's the angle of bent? Well, here's the thing. It looks like a tetrahedron, but it isn't. The lone pairs take up too much space. Those are electrons next to each other, not up and down. So lone pairs take up more space, which pushes the bent angle down a little bit. So what you're going to see in the shape is that these bonds get pushed down. And when that happens, my angle is actually not 109.5 anymore. We are less than 109.5. So that's my angle. And if we look at hybridization, I got 2 bonds. I got 2 lone pairs of electrons. That's sp3. 4 total regions of electrons, 2 bonds and 2 lone pairs. Add them together, you get 4. 1 s, 3 p's. That's how that one works. So I'm a bent shape. I'm 109.5. And I am sp3. Cool. We're almost done. We're going to do NF3 and then OF2. These are a little tougher, but you can do it. N has 5 valence electrons. That one's going to go in the middle here. Let's drop again. Here we go. N goes in the middle. N has 1, 2, 3, 4, 5 valence electrons. Now, you can already see this. I have a lone pair, and because there's 3 F's here, I need 3 bonds. Nitrogen has 5, and if it wants 8, it needs 3 more bonds. So what are my 3 bonds? They're all going to go where the loners are. So this lone pair up top is making a point up top. It's going to be very like a pyramid. Let's connect the F's. I have F, 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 and I need bonds. So let's connect them. Bond, bond, bond. Now what really happens is these lone pairs are going to push the F's downward. So my shape is going to look pyramidal, and that's the shape we have. So I have a sphere, and in the sphere I have a lone pair up top, I have an F, I have an F, and I have a third F right there. So this is your pyramid. There are 3 at the bottom, again, making like a tripod. So the 3 at the bottom are a triangle. I'm a triangular pyramid. And a triangular pyramid is going to have a bond angle, again, that's less than 109.5. Because again, that lone pair is shoving the bonds down. That's what's going on there. And the nice thing is, for hybridization again, 1 lone pair plus 3 bonds, we're back to 4 regions of electrons. 4 regions of electrons means 1s, 3 p's to get 4 total regions, sp3. So that's sp3 hybridized. sp3, done. So that is NF3. The final one, OF2, is going to look exactly like H2S. We're going to put O in the middle, kind of like water, and the O is going to have 6 valence electrons. So oxygen in the middle with 1, 2, 3, 4, 5, 6. Again, I drew that like that because the lone pairs are going to go next to each other. This is going to be another bent shape. Fluorine has 7 and wants 1 more, so fluorine can only bond singly. Oxygen has 6, it wants 2 bonds. We're going to put 1 bond over there and 1 bond over there. Remember, fluorine cannot double bond because fluorine has 7 and only wants 1 more. So, here we go. Let's bond F and F. And I've been lazy, but I'm going to draw the valence electrons around F. So, F, 1, 2, 3, 4, 5, 6. There's your 7th, and there's the 8th that it's sharing. If I go back, I'll do the same thing here. So 1, 2, 3, 4, 5, 6. It looks a little messy, but 2, 4, 6, and then a 7th one right there, plus the 8th one that is sharing. All right. Hopefully this makes sense. This is another bent shape. I am less than 109.5, and I'm sp3. Hopefully this explains why the shapes are drawn the way they're drawn and why the angles are the way they are. This is all geometry, which we're going to do more of next time. Tune into my next video for polarity. And there we go. Have a nice night. Okay, polarity time. Here we go. Polarity is fun. Basically, polarity is when you're an electron and you're going to be attracted more to a certain element. And if that sounds familiar, that's because it is. It's electronegativity, also known as electron riz. Basically, here's how electron riz works. If you're an electron, pretend like you're at a party and you see like the hottest person you know at a party. Well, you're probably going to go gravitate towards that person. There you go. That's polarization. Electrons are not going to be equally shared in bonds. They're going to like slowly be nudged towards the more electronegative one. And that makes sense. If I'm fluorine, I'm going to be way more attracted by... If I'm an electron and I have to choose between fluorine and hydrogen, well, fluorine over here, I'm going to be dragged a little closer towards it because fluorine is super electronegative. Think politics, right? Polarization is when you've got 2 extremes and everybody's being dragged to one side or another side. So visually, that's how polarization works. Now up here, I have the same compounds as last time, except I wrote the electronegativity differences and the shapes again on the board so that we can see what happens. So real quick before we begin, this is our number line that tells you polarity values. So if the difference between electronegativity of atoms is 0 to 0.4, specifically to less than 0.4, between 0 and 0.4 and not including 0.4, I'm not very polar. There isn't that big of a difference. The electrons don't really know where they want to go. They're going to be more equally shared. This is your magic number. Once 0.4 is hit, between that and 1.7, you're going to be polar, and you're going to be covalent. Now the 1.7 refers to, that's silicon dioxide right there. Anything after 1.7 is going to be ionic. Because think about it, right? Ionic is when the electrons totally just give in to what they want. So if you're polar covalent, you're going to be dragged over and dragged over, but ionic, you're going to be dragged all the way over. So if the difference is high enough, metal and non-metal, you're going to be ionic. So that's how this works. Okay, let's get started. I got my first shape. Here we go, CBr4. Well, that looks pretty tetrahedral to me. I got a difference of, so I got 2.5 and 2.8 for C and Br. That's not a very good difference. That's 0.3, meh, not that polar. The electrons don't know where to go. If you're not polar for the bonds, you got no arrows. So it's a non-polar bond, and you are not covalent, I'm sorry, you're not polar at all. So this is a non-polar bond and a non-polar element. And that's it for polarity for this one. Later you'll see some vectors and we'll draw them out and see what happens. CO2 is my next one. Now, this difference is a little better. So oxygen got a lot more Rs than carbon, specifically with a difference of 1. So oxygen is going to yank those electrons towards it more than carbon. But here's the catch. So let's do this, right? This is polar covalent. My difference between 2.5 and 3.5, that difference is 1. So I fall right in the polar covalent category of my number line. So let's make this polar covalent bond. So I am a polar bond, polar covalent bond. But here's the problem, right? If I have a center atom like this and I'm symmetrical, and if I have electrons in the bond, well, I don't know which one to go to, right? I have two arrows, and the arrows point towards the more electronegative one. So I have one arrow going this way towards this oxygen, and I have another arrow going this way towards that oxygen. Well, okay, if I'm an electron and I'm a puppet, right, and I'm being dragged this way and I'm being dragged this way, think tug of war, being pulled by the same force in two directions. I ain't moving. My arms might be ripped off, but I'm not moving. So we have polar bonds, but our molecule is very non-polar. So this right here is going to be non-polar molecule. If you're linear, or some kind of symmetrical shape, you're going to be non-polar. Let's look at the next one, Cl2. Well, Cl2 is it's a Cl and another Cl. What's the difference of electronegativity? I didn't even bother writing the values. Cl is the same as Cl. Where does the electron want to go? It doesn't know. It's going to be equally shared. So for Cl, I am going to be nonpolar for both bond and molecule. I'm nonpolar bond and nonpolar molecule. Going to my final three, I have H2S. Now, H2S is bent. This is going to be weird. My difference here, 2.1 and 2.5, my difference between those two is 0.4. That's our magic number. If we're at or above 0.4, we are polar covalent. So this one's polar covalent. And the cool thing about this one being polar covalent is that the bonds, cancel that please. Now, even though this is polar covalent, we're going to see if, nope, cancel that. So these bonds are polar covalent. Let's see if the molecule is polar. So I got two bonds and two lone pairs. Now, lone pairs, they're not shared. There's no arrow with lone pairs because they're not polarizing electrons. Lone pairs are just there. They're there to affect the shape and nothing else, which means I got two arrows. Now, sulfur here is my more electronegative one, so my arrows are going to go up towards the sulfur. And if I have one going this way and one going this way, and I'm a puppet and I'm being dragged kind of upward, that's going to be my final dipole direction. So I got one this way, and I'm going to be yanked up. The left and right cancel out, but not the up and down. So my dipole looks like this, and that means I am a polar molecule. NF3 is going to be similar. So I got a lone pair up top on that pyramid. That lone pair doesn't have any arrows. So my arrows this time are going to go towards the F's because, well, guess what? F is like the most electronegative element. Fluorine's living a good life here, so it's going to go 1, 2, 3. And if I have 3 arrows, and they're all pointing down-ish, sort of, left and right cancel out. Again, I'm being pulled, and I'm being pulled down. That is a polar molecule. So it's polar covalent bonds with the dipole going down and making it polar covalent as a molecule. So we're almost done. Let's take a look at OF2, right? I'm bent. So if I'm bent, again, I got 2 different directions. My electronegativity difference is 0.5 between O and F. So it's going to be polar bonds. The bonds are going to go, the arrows are going to go towards fluorine, again. So this time I have 2 arrows with the downward dipole, and I'm going to be polar as a molecule. So there you go. Something else to look at is if CBr4, if this was polar, the arrows would cancel out because it's symmetrical. So if these were polar bonds, you'd have 4 arrows all tugging on you 4 different directions, and you'd be a non-polar molecule. That's why like CH4 is methane. It's a kind, like the more C's and H's you have, the more fatty you get as a fatty acid. Those are non-polar. So that's what's going on up here. There's some chem for you tonight. Hope you have a good night. Peace out. And don't forget to always have electron riz, especially on Wednesday. All right, see ya. Hey everyone, you guys get a treat. It's a 2-hour delay, and of course, well, guess what? I didn't know it was, so I'm here anyway. And to waste some time and to help you learn, I'm going to teach you polarity. Again, if you missed class or something, or you just don't know polarity very well, this is how polarity works. So I'm going to use the example HF because it's extremely polar. Polarity refers to a difference in electronegativity where there's going to be electrons moving towards the more electronegative atom, and then we get partial charges coming out of it. So something very interesting about polarity is that there are partial charges, but overall you're not charged. So that's really important. Polarity, it does not refer to actual charges, it refers to like partial charges. So if you think politics, you got 2 sides of the political argument, right? If this circle here is your political argument, right? Then the opinions are going to be divided. And if you're polarized, you're either one extreme, and I'll denote that in positive signs, or you're the other extreme, negative signs. If you think about like almost any, like a balloon, pretend this is a balloon. If you rub that on your hair, then half of it gets negative and half of it gets positive because the electrons move in the balloon. Well, guess what? That doesn't mean that the balloon is overall charged. Overall, this is no charge, but it's polarized. Half of the balloon is more partially positive, and the other half of the balloon is more partially negative. So if I have H and F right here, my electronegativity value of H is 2.1, and my electronegativity value of fluorine is 4. Now this means that this is so it looks like it should be an ionic bond, but this is an exception here. H and F are actually covalent because H doesn't like just giving away its electrons. However, this is going to be extremely polar. So what you get is a bond where the electrons want to go more towards fluorine. So I'm going to denote that with an arrow here. And when we do arrows, it just refers to which direction the more electronegative atom is. If you're not polar, no arrow, no vectors, no dipoles, no nothing. So the arrow refers to the direction. We call those vectors or arrows. And the dipole refers to the final direction of everything. So once you cancel things out, well, there's only one arrow here, so your dipole is going to go this way, and you're polar. This is another visual representation of the actual, like, orbitals. So H here is a sphere because it's the very first element, and F here is actually sp3 hybridized. So there is no central atom, but I'm just showing you that F here and H have different hybridizations. H can't hybridize because it's just a sphere. F would have sp3. So F has one region of electrons where the bond is, and then 3 lone pairs. So 4 regions of electrons, sp3. If you look at the bond, remember bonds are when the orbitals overlap. That's where the pairing up of electrons happens. If you look here, the electrons don't pair up in the middle. They pair up closer to the fluorine. And because of that, you're going to get partially negative charges where the fluorine is, and partially positive charges where the H is. Now notice, right, it doesn't leave the overlap. Like the electrons don't actually go at the fluorine's nucleus at all. They're just kind of invading fluorine's outer shell. So this pairing up here, it can't go beyond fluorine's outer shell. So what it looks like with your charges, you have hydrogen being partially positive. This delta refers to partial charge. And then your fluorine is going to be partially negative. Delta negative. That little swirly D is of delta sign. All right? So there you have it. That's polarity. Hey guys, so last video in my series here, this is hybridization. It's a complicated topic. You're not going to need to know it for the test, but it's very useful to understand for bonding. So I'm going to go through it with you. We're going to have 4 different elements here. And what I showed you is what the valence electrons start to look like. This is not how it looks like in bonding. And the reason for that is hybridization. So when we look at hydrogen, hydrogen only has 1 valence electron. So there's really no way to hybridize it because hybridization is about mixing of orbitals to make a hybrid orbital. When you bond, you have s orbitals and you have p orbitals. The thing is, you can't use both like separately because s is a sphere and p is a dumbbell. So you have to merge them to make equal bonds. And that's what hybridization is. Otherwise, it doesn't work because there's no symmetry. Well, hydrogen is just 1s2. I'm sorry, 1s1. Because hydrogen is 1s1, there's no p orbitals in hydrogen at all. There's no way for this electron to go anywhere. So there is no hybridization in hydrogen. So I'm going to cross all of this row out because hydrogen can't hybridize. Beryllium is a different case. So beryllium, remember beryllium is one of those exceptions where it makes a covalent bond. So regular ionic bonds do not hybridize. There's no shape, there's really no structure, it's just kind of like that. It's that alternating crystal electronegativity, electric values. So we look at beryllium, and beryllium has 2 valence electrons, right? 2s2. I paired them up here, and I paired them up here. The thing is, that is not how beryllium looks in bonding, because beryllium wants to share its electrons. The problem is, beryllium can't share its electrons if they're already paired up like this, because there's no room to get a buddy. If you want to share in the sphere, then your sphere can't have 2 electrons. It can only have 1 electron so that you can get a friend and then share. So what do? Well, there's this thing called promotion where the electron actually jumps up in energy and it's going to move from my s orbital up to my p orbital. So what happens here is I actually get a new hybrid orbital. And the valence electrons on beryllium are going to move. So here's how this works. I have beryllium, and the electrons on beryllium are going to spread out. So these 2 s's are going to break up. That's sad. They're going to break up and cry and want to share now because they're lonely. So we're going to put one on the right one on the left. And any time that beryllium or any atom has a loner electron, that's where the bond's going to happen. Because covalent bonds share electrons. If you're a loner, you're going to be a bond. So you connect the dots, if that makes sense. You can't bond a pair. That's a lone pair. So beryllium is now going to look like this. And what happens in promotion is you get all 4 lines merging. Your S line here and 3 of your P lines all merge together. So here we go. 1, 2, 3, 4. And we're going to call this S and P together, but we got to count first. So we get 2 electrons. 1 was from the S, and 1 are in the P's. So we're going to call this sp hybridization. So my hybridization here is sp. And the shape would be like 50% S character and 50% P character. So it's going to be halfway between a sphere and a dumbbell. So that's what the bond actually looks like. So if I do the shape, I have 2 sp orbitals. Beryllium is going to go in the middle here. And you're actually going to get like this sort of spherish dumbbell shape. And you're usually going to be linear with sp hybridization. So there you go, that's sp. Now another way to do it is you count the region of electrons. Well look, Be has how many bonds it wants to make? Well, it's going to bond 1 on this side, 1 on this side. 2 bonds, 2 regions of electrons, sp. There's 1 S and 1 P, and when you add those 2 together, you get 2. So that's how you do it more basically. Now we're going to go to boron. Now boron again, 2s2, so I pair up these 2. And then this 3rd valence electron is lonely. It's a p electron. Just like last time, I can't bond a pair. So I have to split. And if you remember from BH3, the 3 electrons are going to surround boron and make a triangle. Well, how does that happen? Again, this electron here has to jump to a new spot, to where there's a blank orbital. So now everybody's by itself and can bond. So how does this work here? We're going to get another 4 lines here. 1, 2, 3, 4. And boron will look like this. Boron, 1, 2, 3. It'll make a triangle. That's your planar triangle. Now, how do you do the hybridization here? Again, we're going to count how many regions of electrons there are. We're going to bond here, we're going to bond here, and we're going to bond here. So 3 bonds, no lone pairs. So 3 bonds means 3 regions of electrons. 3 concentrated regions of electrons. So here you go. sp2 now, because I have 3 regions of electrons. 1 in the S, 2 in the P's. If you look, after this one moves, you have 1 in the S, 2 in the P's. So sp2, hybridization. 1, 2, 3 electrons. Again, these are your spin. These are your half arrows if you don't know what these are yet. All right, go on to hybridization. sp2, atom in the middle. Now, this time you're going to have about 1/3 S character and 2/3 P character, because now you have 2 P's and only 1 S that are hybridizing, that are merging. Again, hybridization is a merging of orbitals. So now you're going to look a little less spherical and a little bit more dumbbellish. So you're going to look like this. Little bit less of a circle. Doesn't have to be perfect. But this is what BH3 would look like, and then your H's would go around and bond. Cool. Final one for the basics. So carbon has 4. Again, I paired up the first 2, and then I have 2 loners. Well, carbon wants to make 4 bonds. And if carbon wants to make 4 bonds, then you're going to need this electron moving all the way over here. Again, when that happens, the carbon is going to spread out. So you're going to get 1, 2, 3, 4. Those valence electrons now spread out. And so now you have 4 regions of electrons for 4 bonds, and that's going to be sp3. So you have 4 lines. This time they're all filled. So you're going to be sp3.
And now your shape is going to be 3/4 p character and like only 1/4 as an S sphere shape. So it's going to look even more like a dumbbell now. So I'm going to exaggerate it with like more of a ovalish shape. They're still not perfect dumbbells, but there you go. That's your tetrahedron. Carbon's in the middle. And then, I don't know, HCl, whatever you have on the outside is going to bond with it. So there you go. That's how you do hybridization.